Welcome to the final lecture in our series on diagnostic tests. Previously, we looked at how to evaluate a test kit and how to diagnose an individual animal. Now we scale up. We are leaving the exam room and entering the field. Veterinary medicine differs from human medicine primarily in its emphasis on the herd or population as the biological unit. When you are managing a national eradication program for bovine tuberculosis or verifying that the poultry flock is free of avian influenza for export, the question changes. We are no longer asking, is this specific animal infected? We are asking, is infection present in this population? To answer this, we rarely rely on a single test. Single tests have inherent error rates that are acceptable for an individual but disastrous when multiplied across 10,000 animals. Instead, we combine tests into strategies, serial and parallel, to manipulate the probability of error. We will also encounter a statistical phenomenon that counterintuitively makes good tests perform poorly when applied to large groups, known as the herd specificity collapse. Finally, we will cover the economics of pooled testing and the math required to certify a zone as free from disease. Before designing a program, you must define your goal. Are you screening for a disease introduction? If so, you need a rule-out strategy. Your goal is to catch every single case. In this scenario, a false negative is a disaster that could spark an outbreak. Therefore, you prioritize sensitivity above all else, accepting that you will have some false alarms to sort out later. Conversely, if you are in the final stages of an eradication program, you need a rule-in strategy. Here, every positive result leads to slaughter. You cannot afford to kill a healthy animal or impose trade restrictions falsely. In this context, you prioritize specificity to ensure that a positive result is truly a positive. Let's look at how to combine tests. The first method is parallel testing, which means you run test A and test B at the same time on the same animal. The interpretation rule is straightforward. The animal is classified positive if test A or test B is positive. This approach is used when the priority is to minimize missed cases, such as in emergency screening or at quarantine stations. Because a true case only needs to be detected by one of the tests, net sensitivity increases. It captures infections that might be missed if you relied on a single test. The trade-off is that false positives can also come from either test, so the overall probability of a false alarm rises. As a result, net specificity decreases, and positives from parallel screening often require confirmatory testing when the operational consequences of a false positive are high. Let's break down the math for parallel sensitivity. The formula assumes the tests are independent, meaning the reason one test fails is unrelated to why the other fails. The logic focuses on failure rates. 1 minus sensitivity equals the false negative rate, the probability of missing a case. To miss a case in a parallel strategy, both test 1 and test 2 must fail simultaneously. We calculate this by multiplying their individual false negative rates. We then subtract that result from 1 to find the probability that at least one test succeeds. Imagine we have two tests, and each one has 90% sensitivity. That means each test has a 10% miss rate, which is 0.1. In parallel testing, we classify an animal as positive if test 1 or test 2 is positive. So the only way we miss a truly sick animal is if both tests miss it at the same time. If the tests make errors independently, the chance that both miss is 0.1 times 0.1, which equals 0.01. That means there is only a 1% chance of missing the disease. So the net sensitivity becomes 1 minus 0.01, which is 0.99 or 99%. In other words, parallel testing turns two moderately sensitive tests into a very high sensitivity combined strategy, which is why it's used when the priority is to minimize false negatives. The second method is serial testing, which acts as a filter. This is the standard workflow in most veterinary clinics. You run a cheap screening test first. If it is negative, you stop. If it is positive, you run a second, more specific test to confirm. This strategy maximizes specificity. To be falsely diagnosed, a healthy animal would have to trigger a false alarm on the first test and the second test, which is very unlikely. However, this system is leaky. If the first screening test misses the disease, the animal is sent home. The second test never gets a chance to find it. Therefore, serial testing always reduces your overall sensitivity. Here are the formulas for serial testing. For net specificity, we use logic similar to the parallel example. We multiply the false positive rates of both tests to find the probability of a double false alarm. This probability is tiny, so our specificity becomes very high. For net sensitivity, the math is simple multiplication. For an animal to be correctly identified, it must pass the first hurdle test 1 and the second hurdle test 2, since probabilities are always less than 1. Multiplying them results in a smaller number. This proves mathematically why serial testing reduces your ability to find disease. Now let's see the impact on sensitivity. Suppose our screening test detects 90% of cases, and our confirmatory test also detects 90%. In a serial protocol, a sick animal is only found if it tests positive on both. 0.9 multiplied by 0.9 equals 0.81. Our system's total sensitivity has dropped to 81%. We are now missing almost 1 in 5 cases. This is the calculated risk we take to ensure that we never falsely condemn a healthy animal. We now shift our focus to herd-level testing. In surveillance, we often test a sample of animals to determine the status of the entire herd. The definition of a positive herd is arbitrary, but the standard rule is called K equals 1. This means if we find a single positive animal, we classify the entire herd as infected. While this sounds logical, it creates a statistical problem. Herd sensitivity and herd specificity behave very differently than the sensitivity and specificity of the test kit itself. As we test more animals, the laws of probability work against us in surprising ways. There is a critical concept for fieldwork known as the specificity collapse. When you test a herd, you are technically running a parallel test on n animals. Here is the problem. Every time you test a healthy animal, you roll the dice on a false positive. If your test is 98% specific, you have a 2% chance of a false positive per cow. That sounds low. But if you test 50 cows, you are rolling that dice 50 times. The herd specificity formula represents the probability that a truly disease-free herd will be correctly classified as negative when you test a given number of animals. It is built from repeated multiplication of the same individual probability. At the animal level, specificity is the probability that one healthy animal tests negative. If you test multiple animals and assume the test results are independent, then the probability that all tested animals are negative is the animal level specificity multiplied by itself once for each animal tested. So herd specificity equals animal level specificity raised to the number of animals tested, because a herd is only called truly negative if every tested animal returns a negative result. To make it clear, let's plug in the numbers. We test 50 cows with a 98% specific test. 0.98 multiplied by itself 50 times equals 0.36. This means there is only a 36% chance that this completely healthy herd will test negative. There is a 64% chance that we will find at least one false positive reactor and wrongly quarantine the farm. This explains why we see so many spurious outbreaks when we conduct massive surveillance campaigns using imperfect tests. How do we fix the herd specificity collapse? We change our definition. Instead of saying one strike and you're out, we define a positive herd as one having two or more positive animals. Statistically, getting two false alarms in the same sample is very rare. This simple change restores our herd specificity to acceptable levels. However, it makes it harder to detect a herd that is just starting to get infected, where there might truly be only one positive cow. To compensate for the loss of sensitivity caused by raising the cut point, we must test more animals. This is a three-way tug of war between sample size, cut point, and design prevalence. When you increase cut points from any positive to at least two positives, you reduce the chance that a truly negative herd is misclassified, higher herd specificity, because random false positives are less likely to reach the threshold. But you also make it harder for a truly infected herd to be detected, especially when prevalence is low or infection is clustered, because you now need to find at least cut point infected animals in your sample. Increasing the sample restores herd level sensitivity because it increases the expected number of infected animals sampled and reduces the chance that you miss infection simply by sampling. Veterinary surveillance is often limited by budget. Pooled tool testing is the economic solution. Imagine we need to test 1,000 milk samples. Running 1,000 separate PCR tests is too expensive. Instead, we can mix the samples into batches of 50, which run 20 tests on these pools. If a pool tests negative, we have cleared 50 animals for the price of one test. If a pool tests positive, we know the infection is somewhere in that batch. We go back and test those 50 animals individually to find the culprit. This strategy saves thousands of dollars in low prevalence populations. The risk with pooling is dilution. Imagine one cow has a low level of virus in her milk. If you mix her sample with milk from 49 healthy cows, you dilute the virus by a factor of 50. If the concentration of the virus drops below the machine's limit of detection, the pool will test negative. You will have missed the case entirely. Therefore, you must never pool samples unless you have validated that your test is sensitive enough to detect a single weak positive sample, even when it is heavily diluted. What do we do when a new disease emerges and we don't have a perfect gold standard test to compare against? We use a statistical method called latent class analysis. We take two imperfect tests, ideally ones that look for different things, like an antibody test and a DNA test. We run them on two different populations. The computer model analyzes how often the tests agree and disagree. By solving a set of probability equations, the model can estimate the sensitivity and specificity of both tests without ever knowing the true status of any single animal. Finally, let's discuss certifying a zone as free from disease for international trade. Scientifically, you can never prove zero risk unless you test every single animal in the country, which is impossible. Instead, we use probabilistic freedom. We design a survey to detect a specific level of infection called the design prevalence. For example, we might aim to detect the disease if it infects at least 1% of the population. If we look hard enough to find that 1% and find nothing, we certify the country as free within those statistical limits. How many animals do we need to test to claim freedom? We use the formula of the binomial detection sample size for demonstrating freedom or detecting at least one case. Here we are assuming a perfect test and independent sampling, which relies on logarithms. However, there is a simple shortcut called the rule of 3. To be 95% confident, you divide the number 3 by your design prevalence. If you want to detect a disease present at 1%, you divide 3 by 0.01. The result is 300, so if you test 300 randomly selected animals and find 0 cases, you can statistically claim that the prevalence is below 1% with 95% confidence. To summarize our lecture, a single test result is just a data point. To build a program, we combine tests. We use parallel strategies when we want to rule out disease in quarantine, and serial strategies when we want to confirm disease for eradication. We learned that testing large herds requires adjusting our interpretation to avoid false alarms. We discussed how pooling samples can make surveillance affordable provided we watch out for dilution. And finally, we learned that freedom from disease is the calculated statistical confidence, not an absolute truth. Thank you for your attention.